how in the world do chemists keep track of millions of different substances without getting them all mixed up? Well, it's all thanks to a universal language, and today we're going to break down the simple but really powerful rules of how to speak it. You know, you're actually surrounded by this stuff every single day. We're talking about the sodium chloride in your salt shaker, the sodium bicarbonate in your baking soda, and maybe even the calcium carbonate in your antacids. But baking soda isn't a scientific name. That brings us to the core issue. How do you name these things so that a chemist in another country knows exactly what you're talking about? Common names just don't cut it. You need a system that works every single time. All right, so here's our game plan. We'll start with the most important question you have to ask first. Then we'll dive into the rules for ionic and molecular compounds, take a quick look at acids, and wrap up with a really powerful story about why all of this matters.
You know, the entire process of naming any inorganic compound, it all boils down to one critical decision right at the start. Think of it like the main trunk of a decision tree that's going to branch out from here. And this right here, this is our map. The very first question is always, is it ionic or is it molecular? Once you answer that, you're already on the right path. The other questions just guide you the rest of the way. This system gets rid of all the guesswork.
Okay, so let's head down that first major path on our tree, ionic compounds. These are usually what you get when a metal and a nonmetal get together.
Now for the easy ones, the compounds where the metal always has the same charge, the rule is a piece of cake. Seriously, you just say the metal's name, then you say the nonmetal's name, but you swap its ending to "ide." So NaCl? It just becomes sodium chloride. It's really that straightforward. But here's where we hit a little snag. What happens with metals that can have more than one possible charge? Like iron. It can bond with chlorine to make two totally different compounds. So what do we call them now?
And this is a huge deal. If we call both of them iron chloride, how does anyone know which one we're talking about? They don't. And in chemistry, that kind of ambiguity can lead to some really big problems.
The solution, though, is actually pretty brilliant in its simplicity. It's called the Stock system. We just add a Roman numeral in parentheses right after the metal's name to tell everyone what its charge is. It's a simple little trick that clears up all the confusion.
And just like that, our problem is solved. FeCl2 is now iron 2 chloride because the iron has a 2+ charge. And FeCl3 becomes iron 3 chloride for the 3+ charge. The names are now perfectly crystal clear. Okay, let's put this into practice. Your turn. Based on what we just went over, what's the systematic name for CrCl3? Let's walk through it together. So let's do a little detective work here. We know that a chloride ion always has a -1 charge. And looking at the formula, we can see we've got 3 of them. So that's a total negative charge of 3. Now, for the whole compound to be neutral, that single chromium ion has to have a +3 charge to balance everything out. And there it is. The correct systematic name is chromium 3 chloride. That little Roman numeral tells any chemist, anywhere in the world, exactly what's going on with that chromium ion. Okay, let's go back to that fork in the road and take the other path, molecular compounds. Now these guys are formed between nonmetals, and they play by a completely different set of rules.
With molecular compounds, the whole game changes. We're not balancing charges anymore. These atoms can team up in all sorts of different ratios. For example, carbon and oxygen can form CO, or they can form CO2. So the name itself has to do all the heavy lifting and tell us exactly how many of each atom we have.
And the tool we use for this is a super handy set of Greek prefixes. You know, mono for 1, di for 2, tri for 3, and so on. It's basically a built-in counting system right in the name. So using these, CO becomes carbon monoxide, and CO2 is carbon dioxide. Oh, and a little pro tip. We usually drop the mono if it's on the first element. For something like N2O4, di tells us 2 nitrogens, tetra tells us 4 oxygens, so we get dinitrogen tetroxide. The name is literally the recipe for the formula.
All right, time for a quick but really important side quest. We need to cover the special rules for one very important group of compounds, acids.
Acids basically come in 2 main flavors. First, you've got binary acids, which are just hydrogen plus one other nonmetal. The pattern is always hydro plus the root ending in icid acid, so HCl becomes hydrochloric acid. The second kind, oxyacids, have oxygen. For these, the name comes from the ion they're made of. If the ion ends in ate, the acid ends in ike.
so sulfate becomes sulfuric acid. If the ion ends in ite, the acid ends in us, so sulfite becomes sulfurous acid. It's just a simple pattern of swapping the endings.
So, I know this might feel like just an academic exercise in getting names right, but as we're about to see, this language of precision, well, it can have some really profound real-world consequences.
You've probably heard of the case made famous by the movie Aaron Brockovich. It was a huge, real-life lawsuit over contaminated drinking water. And the entire thing, literally all of it, hinged on the chemistry of one single element, chromium.
And this slide right here shows exactly why this naming system is so critical. On the left, you've got chromium-3. It's an essential nutrient. You can find it in vitamin supplements. But on the right, you have chromium-6. This is the highly toxic carcinogen that was leaking into the town's water supply. The only difference between a nutrient and a poison here is the charge of the ion, a detail that is communicated entirely by that one little Roman numeral.
This whole case is just a stark reminder that chemical nomenclature isn't just about passing a test. It is a language of absolute precision, where the difference between a 3 and a 6 can literally be a matter of life and death. It really makes you stop and think, doesn't it? What other massive consequences might be hiding in the small details of science that we might be overlooking?